Okay, it's 9 o'clock, so let's begin here. Project number 3 course is due on Tuesday at noon. Test number 3 is Wednesday, December 2nd. Note that we only have one more class after this one before the test, so that means our next class on Monday, December 2nd, we will spend time reviewing. So please come prepared to ask questions if you have them. Are there any questions at this time before we get going? Okay. We're talking about logistic regression. And right now what we're doing with logistic regression is just giving you enough background, essentially as quickly as possible, so that we can get to the purpose of us using logistic regression. And that is to predict the population of an observation. And with logistic regression, we can only use it for when you have two different populations. The next section, we'll talk about what's called multinomial regression, and that will allow us to extend it to practically as many populations as would be of interest to us. Okay, so just to review a little bit here, this is what our model looks like. Or let me first state first of all that our response variable, think of it in the regression-like setting, is either equal to a 0 or a 1. So for us, you can think of a 0 as being one population and a 1 being another population. Typically, when people work with logistic regression, though, they will typically refer to the y equal 1s as successes and the y equals 0s as failures. And I will do the same thing here. So we have successes or failures. And what we're interested in doing is modeling then the probability that y is equal to 1. And we denote this probability by a simple symbol, pi. Y has a Bernoulli distribution with then the corresponding parameter pi. And this is what our model looks like. There's two different ways to write it. You can set pi equal to e to a linear combination of the betas with the x's over 1 plus e to that same linear combination. That nice little transformation of this linear combination of the betas and the x's guarantees that pi will always be between 0 and 1, which makes sense for probability. Now, using some algebra then, what we can do is we can write then on the left-hand side the log of pi over 1 minus pi, which is often abbreviated with logit of pi. It's just notation, but that's what you will typically see people write. And then you set that equal then to the linear combination of the betas with the x's. Okay, so that's what our model looks like. So now we need to talk about, well, how do we estimate the model? We estimate the model using maximum likelihood estimation. We've seen maximum likelihood estimation before. And in fact, we've seen it in the context of a Bernoulli distribution before when we were talking about, when we first introduced maximum likelihood estimation in the factor analysis section. So this is what our likelihood function essentially looked like in that factor analysis section. Please note this small little change there. The little n should have been a capital N to correspond to our notation, or we have capital N as our sample size. Now the difference between what you see in this part right here to what you saw in the factor analysis section is that now we have a subscript on the pi. Subscript, we're going to use r. Remember, we typically use r to note a particular observation. So what this is saying then with this likelihood function then, that pi can change can be different for every single observation. Also then, what the difference between what we saw in the factor analysis section and now, what we have is now our logistic regression model is then telling us what the expression of pi is and how it can change as a function of our, in this case, explanatory variables, or independent variables, or covariates, whatever you want to call them. So again, we have n possible different pi's. And we essentially simplify the problem. Instead of having to estimate n different parameters, we only have to estimate p plus 1 parameters, the betas. So because of that, then we can rewrite then the expression that you saw on the left-hand side for that likelihood function. We can rewrite it as so. And then what you do with maximum likelihood estimation, you find the log of the likelihood function. You come up with some more simplifications as well, and do some algebra. And this is what your log likelihood function looks like. Obviously, it's kind of messy. But what you do then is you try to find the betas that maximize this log likelihood function. And those are your maximum likelihood estimates. I will denote the maximum likelihood estimates in a simple form by beta hat. So once you get then these maximum likelihood estimates, then you can put them into your model to get your estimated logistic regression model. One way we can write it then is what's shown there, where now we have pi hat on the left-hand side. Please note that if ever on a test I ask you to write out the estimated logistic regression model, and if you do not put a hat on the pi, you will have points taken off. There's a difference between pi hat and pi. So again, we maximize this likelihood function as a function of the betas. Those betas that maximize it are the maximum likelihood estimates, the beta hats. Well, what's the actual numerical process that's used to maximize the likelihood function? Well, unfortunately, there's not a nice little closed form solution for what beta hat 0, what beta hat 1, what beta hat sub p are equal to. You cannot actually write it out, except for in very special cases. So because of that, you have to use what are called numerical iterative methods. And we've discussed those way back with the factor analysis section as well. And so we use these numerical iterative procedures or methods to find the maximum likelihood estimates. And since it's an iterative procedure, what you're hoping is that for every, let's say, step in the iterative process, you get better estimates of the beta hats. And eventually you come to convergence, meaning that the beta hats for one iteration are just about exactly the same as for the previous iteration. So you have found those maximum likelihood estimates. Now there will be cases where convergence does not happen, and we will talk about that at the end of the section. Okay, so that takes us then to an example. So just to get us exposure to how we actually estimate a model in R, we're going to use, again, the place-kicking data set here. And so what I'm interested in doing is estimating this particular model. Please note the little small change there. It's on page 10. I'm interested in estimating that model. And what I've done is simply replace the x's with what the actual variables are for our data set. That's okay to do. If you don't want to replace the x's, that's okay, as long as you define what the x's are. So I'm trying to estimate log of pi over 1 minus pi as a function of then weak, distance, wind speed, or I should say just wind, and so on. Okay. Let's estimate that model. So I read in my data, and then to estimate the model, I'm going to use a function called GLM. We've seen the LM function before for regression analysis. LM stood for linear model. Now the G of GLM stands for generalized linear model. So we can see that, our logistic regression model is essentially a generalization of a regular old regression model. So that's where the GLM comes from. And we use a very similar syntax to what we saw with the LM function. We specify in the formula argument what our model is in the correct R syntax. If you remember, our response variable is good. Why it's good is equal to 0 for a failure, good is equal to 1 for a success. Then tilde, separate the response variable from the independent variables. I put in there all my different independent variables. I separate them, of course, by plus signs. And then I specify where my data is. And then lastly, an argument that we did not have with the LM function specifies, well, what kind of generalized linear model do we want? There's actually a lot of different kinds of generalized linear models. We're going to talk about one, the logistic regression model. And so you can think of it, you have a family of different kinds of generalized linear models. That's why we have an argument called family. And we specify, first of all, the syntax is kind of weird here, specify, first of all, binomial. Well, remember our response, y equals 0, y equals 1 is Bernoulli. So that's where the name binomial comes from. Bernoulli is a special case of a binomial. And then we have another argument in parentheses here called link. Link equal logit. Well, where that comes from then, it's probably fairly obvious. Go back to when we actually use that notation. Eventually, I'll get there. Oh. There we go. So what links then pi to this linear combination of the betas with the x's? Well, this function that's referred to as the logit function. So that's where link equal logit comes from. So I'm going to put the results into an object called mod.fit. And let's just print off mod.fit here. And you can see a little bit of the information of what's actually stored in mod.fit. What you see there is, although it's kind of cut off on the screen, unfortunately. Move this over. What you see there is something called coefficients. These are the beta hats. So beta hat 0 is 4.78. We can get a better set of information or a better summary of what's inside this mod.fit by using the summary function. And then we get the usual kind of output that you would expect from using like a regular old regression model. In particular, here's a table of coefficients, which again you can see. Here's the beta hats. So beta hat 8 is negative 0.63, the coefficient on wind. Let me come over here to Word, so I can write on my my screen here. So here are my beta hats. We call beta hats of I, because we have I equals 0 to 8. And then we have a standard error column. This is the estimated variance of a beta hat square rooted. Then we have a z column. This is going to allow us to perform a hypothesis test to test whether or not a particular variable is important to include in the model. So it's just the standard beta I is equal to 0 versus beta I does not equal 0. And in my test statistic, we'll call it z because we're going to actually use a standard normal approximation for it. Is beta hats of I minus 0 over the square root of the estimated variance of beta hat I. Okay? So we use a standard normal approximation with it. So if we have test statistics that are between maybe negative 1.96 and positive 1.96, we don't reject HO. Outside, we reject HO. We can also come up with a p-value, and that's what the last column basically represents. Or I should say it does represent. If I have a random variable A that's distributed in normal 0, 1, then that p-value is the kind of p-value that you calculated before in a stat 801 kind of course for a two-tailed test. 2 times the probability the random variable is greater than the absolute value of the test statistic. So for example, we can see that weak has a p-value of 0.2. So would we typically reject or don't reject HO? don't reject HO, meaning that given all the other variables are in the model, there is not sufficient evidence to indicate that weak is indeed important. How about for distance? Do we reject or don't reject? We reject. So that's 2 times 10 to the negative 14th power. So that means it's very, very small, that p-value, saying that there is sufficient evidence to indicate that distance is important, given all the other variables are still in the model. So, if you've ever heard of the term walled tests, these are walled tests here. We can also do likelihood ratio tests to test exactly the same hypotheses. Typically, likelihood ratio tests are better in this situation than walled tests are. Given, though, that we have a very large sample size here, typically there's practically no real difference between the two tests in terms of if one's better or worse. To do likelihood ratio tests, we can use a package called CAR. It stands for Companion to Applied Regression. It's actually a package written for a book called Companion to Applied Regression. And it provides a nice little function called ANOVA. And notice the capital letter there. Where the term ANOVA in this case comes about, we're not actually using analysis of variance, but we're doing a lot of similar tests that you would in a regular old ANOVA setting that you would have in Stat 801 or 802, so that's where the name comes from. So if I say ANOVA mod.fit, then I get likelihood ratio tests. So you can compare these p-values to what we see above, and you can see that they're pretty close. Again, you're testing the same hypothesis. We can further see the information that's actually stored inside of mod.fit by using the usual names, mod.fit. So mod.fit is actually a list. And so you can see there's a whole bunch of information stored in there. If I were to do mod.fit $ coefficients, we see we get the beta hats. If I do mod.fit $ fitted.values, we do a head on that. You get all the pi hats for the observations in the data set. So for example, for the very first observation, the estimated probability of success for that place kick is 0.94, according to the model. So page 13 then in the notes shows you how you can actually write out your model. So again, if I ever ask you to write out an estimated logistic regression model, this is how you would do it. Just take the beta hats, put them in the corresponding spots, and say logit pi hat is equal to all that stuff on the right-hand side. This would be, for example, the easiest question on the test. So given then this model, then, what happens to the estimated probability of success as the distance increases? Is the probability of success going up or down? Going down, because we have a negative coefficient on distance. Remember the discussion from our last class regarding that. And hopefully that makes sense. You know, as you get farther away from the goalposts, then it's going to be more difficult to make the place kick, or the place kick. So what happens then to the estimated probability of success for a lead change? That's when change is equal to 1, as opposed to a non-lead change place kick. Change is equal to 0. Is the probability of success higher for the lead change or lower for the lead change? Lower, because there's a negative coefficient on there. So that shows, again, there's kind of a pressure effect associated with this. Now, let's actually go back to the output. Those statements that we just made, we have to be a little bit careful about. Now, For distance, obviously we see the p-value is quite small. So yes, there's sufficient evidence to indicate that beta does not equal 0. And given that there's a negative coefficient for that beta hat, then I can say yes, the probability of success does decrease. With change, we have a somewhat small p-value there. So we can kind of say, there is some evidence saying that indeed that the probability of success goes down for a lead change versus a non-lead change cascade. But let's say I ask you the same kind of question about a week. So what happens to the probability of success as week increases, the week of the season? Does it go up or down? It goes down, but you have to be very careful on how you interpret that, because notice the p-value here, 0.2. So you would say don't reject HO for the actual beta for week. So what that means then is that you can go out and take a sample, another sample. You're not necessarily guaranteed that that the beta hat for week will be still negative. It could be positive, because there's really not sufficient evidence to indicate that there truly is an effect. So of course, when you make these interpretations about what happens to the probability of success, you have to take into the context, of course, the results from that hypothesis test. Okay, so page 13 at the top contains something that's important. This first bullet. So again, our good variable in the data set is either equal to a numerical value of 0 or 1. Now what R sees is that, okay, so we have a 0, 1, and corresponding to the way that I introduced you to the model, we want to model the probability y is equal to 1. So our model is in the probability good is equal to 1. So that the pi in our model is the probability of success for us in the context of this problem. But let's say instead, though, instead of having the good variable equal to numerical values, suppose they was equal to character values, such as actually the word success and the word failure. R will still estimate the model. But how do you know that R is modeling the probability of success or the probability of failure? The way you know corresponds to something how we talked about earlier in this course about how R takes into account qualitative variables. It always puts everything into that particular order. And so notice that a failure, F, comes before then the S for success. So the way that R is seeing everything is putting failure first and success, let's abbreviate that, second. And what R would always do, set the first level essentially equal to 0, failure equals 0, and then the first level, then the second level will be the 1. So that's how you know what R is actually modeling. You put it into the order that R has for qualitative variables. And the second level is what R is modeling. Trust me, that can be confusing. In particular, I know, for example, in SAS, Logistic will actually do the opposite. So please be aware of that. Okay. So if you want to know more about place kicking, take a look at my paper on it. That was my very first paper that I ever had published. So now we get to what we really want to do with a logistic regression model, and that is use the logistic regression model for prediction. I want to predict, is this place kick going to be a success or is it going to be a failure, for example. And again, it all starts then with estimating your model, and then in your model you put in your beta hats that you got out from R. Then for any set of x's, you could do some simple algebra and get a pi hat out. And that's going to be your probability of success. Probability y, estimated probability of success. Estimated probability y is equal to 1. Once you have that, then you can use then this model for any observation that you want. Now, how do you make the decision of, should I classify this observation as going to be a success, or predict this observation as being a success, or should I predict it as a failure? Well, here's the most commonly way that it's done. And I kind of brought this up last time too. If the estimated probability of success is greater than 0.5, classify it as a success, or y equal 1. Predict as a y equal 1. If pi hat is less than 0.5, predict it as a failure. Very, very simple. Makes sense. You know, you're making the prediction corresponding to what has the highest probability of happening. Okay? So using 0.5 in this manner, sometimes, not always, I don't think this is necessarily a standard term. But I've seen it elsewhere, and I like to use the term. This 0.5 is used as what I'm going to call a cutoff probability. Because you're cutting off, then, let's say, the successes from the failures at 0.5. So again, I'm going to call this a cutoff probability. But, you know, you don't necessarily need to use 0.5 as the cutoff probability. Especially in settings where maybe you are really, really concerned about making a particular kind of error, such as, you know, the kind of error where you predict a y equals 0 when in fact it was a y equal 1, or vice versa. In those settings, it might make, especially in those settings, it might make sense to use a pi hat different from 0.5, maybe 0.7, maybe 0.2. And you'll see why when we take a look at this now for pretty much the rest of the notes, why that's the case. Because you can really increase then your accuracy for, you know, predicted, let's say, a y equal 1 when it was truly a y equal 1, or predicted y equals 0 when it was truly a y equals 0. You can really increase your accuracy by fooling around with that cutoff probability or moving it around. Again, you'll see more about that. In a tool that we're going to use to make this judgment of what we should use for a cutoff probability, a tool that we're going to use is what's called a receiver operating characteristic curve, or ROC. That's the way that people typically refer to this as. They don't call it the ROC curve, for example. It is an ROC curve. Now, to understand what ROC curves are, we need to talk about things, or something called sensitivity and something called specificity. Okay? These are measures of accuracy for a classification method, such as this. And this takes us then to the HIV testing example that we first saw in the discriminant analysis section. So imagine, again, you have a clinical trial, and you maybe have a new HIV test that you're trying to determine, you know, how good is it? And you're comparing the results to what would be considered a gold standard. That basically gets everything right. But that gold standard might be a lot more expensive to use. So that's why you want to explore these new tests. So, you know, you do a clinical trial, you apply the test to a number of people, and then you're able to put together a table such as this. So in the rows we have the actual results, or the actual, does someone have HIV or not? So yes or no. And just for simplicity, how about if we say yes is a means positive, a no means negative. Now this new HIV test then either is going to give you back results of positive or negative to try to predict the actual results, or the actual outcomes. And what you're hoping then is that the test gets all the true negatives correctly predicted as negative. You're hoping that this new test gets all the true positives correctly predicted as positives. That's what you're hoping. Instead, what will actually happen in practice with HIV tests is that you're going to have to deal with some of the false positives, you could say, and the false negatives. Meaning that a test says that someone is positive when in fact they are truly negative, and vice versa then for the other definition. Okay. So then, in diagnostic testing situations such as this, and then, well, this is where it more originated, but it's used in many other places too. You can focus on then those two correct cells there. And we can start defining probabilities of being in those cells. So we're going to talk about something called, first of all, the sensitivity of a classification method. Simply, it's this. Given, I'll talk about it in terms of this HIV example. Given that a person is actually positive, what's the estimated probability that they're going to be classified as positive? Notice that this is a conditional probability. Another way to word this is that what's the proportion of these true positive individuals does the test actually say are positive? So given positive, truly positive, what's the proportion that are predicted as positive? So that's the sensitivity. The specificity then is kind of then the opposite, where given that an individual is actually negative, what's the estimated probability that they are classified as negative? Again, it's a conditional probability. So, for example, here maybe are the results of the particular clinical trial of question. So in this clinical trial, there were 100 people that were truly not HIV, that were truly HIV negative. I'm sorry, 200 people. And there were 100 people that were truly HIV positive. So obviously this probably wasn't a random sample. It was conducted in the United States. So in this particular case then, given truly HIV positive, the test detected 99 out of 100 as being positive. So then the sensitivity is 0.99. For the specificity then, out of the 200 people that were HIV negative, we got 195 right. So in this case, then the specificity is 195 divided by 200, 0.975. That's how you calculate the sensitivity and specificity of a classification method in general. Of course, the larger these sensitivities and specificities are, the better the classification method is. Ideally, you would like these values to be equal to 1. Now we can look at it from a different point of view. Well, let's talk about the errors. So we can talk about then the false negative rate, which ends up being 1 minus the sensitivity. So again, given positive, what's the false negative in terms of the test that came back was negative when in fact the person was truly positive? Well, the false negative rate would then be 1 divided by 100. That's the false negative rate. You can also talk about the false positive rate as well. So given you are truly negative, then there were 5 false positives. So 5 divided by 200 is the false positive rate. Ideally, of course, we would like then the false positive and the false negative rate to be as close to 0 as possible. Just a little note about my notation here. If you notice, I have like a little hat on top of some of my probabilities. I just decided to introduce sensitivity, specificity, the false positive, false negative rates as estimates so that we could look at that simple table that we saw there. So that's why I put a little hat on top of that to mean it's an estimated probability. So, again, remember too, from your first stat course, when you talked about conditional probabilities, or let's actually do it this way, just to make sure this is clear. You talked about complements in your very first stat course. Let's say you have an event A, then the probability of A is equal to 1 minus the probability of A complement, or A bar. So, you know, some books will, or some courses will put like a little, or superscript C there to mean complement. Some books or courses will put like an apostrophe right next to A. I just put a bar there. Those are the three different ways that people mean the opposite of A, the complement of A. So the probability of A is equal to 1 minus the probability of A complement. Also, we can then think of it in terms of conditional probabilities. You should have seen this too. So the probability of A given B is equal to 1 minus the probability of A complement given B as well. And so you can see, for example, then 1 minus the sensitivity then, here, is equal to 1 minus the probability of a classify positive given actual, not right, given actual positive, which then would be equivalently expressed as probability classified negative given actual positive. Okay? Any questions about that? So what often happens then, or what almost always happens in application, is that you get to a point where you like to be able to increase your sensitivity, if that is the most important thing for you for classification. Maybe you want to increase the sensitivity of your classification method, and the way that you can do that is to change that cutoff probability. Maybe move it from 0.5 to 0.3. You'll see why as we go along. But what ends up happening then is, unfortunately, it will decrease your specificity. Conversely, you might be very, very concerned about the specificity of a classification method. And so you want to increase that. Well, you can change your cutoff probability to try to do that. But when you do that, that will decrease the sensitivity. And so it's kind of a give and take. What values of sensitivity, what values of specificity do you want, or what values you can live with as well. Gosh, it was a long weekend for some people here. I see so many people falling asleep. Is it really this boring? Or just a long weekend? Okay. Anyway, so now to make this judgment then between the sensitivity and specificity, you might think, well, is there some way that we can do a plot that helps us make this decision about what do I want my sensitivity to be and what do I then give up in terms of specificity, or vice versa? And that's what these ROC curves, plots of the receiver operating characteristic curves, that's what they allow you to do. And they are a plot of the sensitivity versus 1 minus the specificity. Remember, that would be then the false negative rate. A plot of sensitivity versus 1 minus specificity at, let's say, all possible cutoff probabilities that you could have. So let's take a look at a demonstration of what this looks like. So on my website, hopefully you have downloaded this already, there is a link to a paper from Scientific American that talked about these receiver operating characteristic curves. This paper came out in 2000. And if you're not familiar with Scientific American, it's a nice little magazine that talks about science, written at a level so that even if you're not an expert in a particular area, you can understand what the article is talking about. And so I strongly recommend that you read the article. First of all, it talks about the origins of receiver operating characteristic curves. It actually came out in World War II in radar detection. If you remember, radar was a new thing back then. And so that's where these curves were, these ROC curves were first developed. But they're really, really used, especially in terms of diagnosing people as having a disease or not. And so this particular example talks about a glaucoma. And they have a possible, let's say, receiver operating characteristic curve for the detection of glaucoma here. And so what you see, first of all, on the y-axis, the article calls true positive probability, which it is, but more people call it the sensitivity, which is what we define. And on the x-axis, you have 1 minus the specificity. So you can see, obviously, both the x and the y-axis go from 0 to 1. Now, what's plotted here, then, first of all, this, I think it's kind of purple, it shows up there, is what a receiver operating characteristic curve looks like. And the way that this plot came about was through, you can imagine, we'll talk about it in a logistic regression context. Actually, these curves can be used in other settings than logistic regression, but we're only going to talk about for logistic regression. Let's say that I had a cutoff probability of 0.2. Then, maybe right there, you find the sensitivity, you find the 1 minus specificity. So, in other words, for, let's say, your data, you apply a cutoff probability of 0.2 to all your observations, and then you get the estimate for the sensitivity and specificity. And maybe that's where the sensitivity minus 1 minus specificity actually ends up being. Then use a cutoff probability of maybe 0.3. Find the corresponding sensitivity, find the corresponding 1 minus specificity. And you keep on going to maybe use a cutoff probability of 0.9. Find the sensitivity, find the 1 minus specificity. Once you do that, then you join all those points with a line, and you get that curve. And so now how you use this curve is this. Maybe you desire, for example, I can't draw a straight line here. Let me do some erasing first of all. So maybe you desire a sensitivity of 0.9. Well, to find what the 1 minus specificity is, go over to the curve, and then you project down, and you can see that you get a 1 minus specificity of about low over 0.5. Well, you might see that and think, okay, I can't deal with that many false positives. So what would happen then if I were to maybe drop my desire for sensitivity down to 0.8? Well, I'm right here on the curve. Oh, look at that. Now I have a false positive rate of about 0.27 or so. I can live with that. Okay, so let's use this cutoff probability, the corresponding cutoff probability, whatever it is, for my diagnostic test. That's how these curves work. So then, ideally, what would the best curve, the best ROC curve look like? A straight line? Yeah, vertical. The best curve would look something like this. It wouldn't actually quite be a curve. That would be the best curve. Because notice that you always get a perfect sensitivity and your false positive rate is 0. That would be ideal. So, to put it another way, first of all, that typically won't happen in most applications. But to put it another way, you want to be as close to that upper left-hand corner as possible. If you're closer you are, the better your classification method essentially is overall. So also, think of it in a different way. Notice as that curve is getting closer and closer to the upper left-hand corner, look at the area underneath the curve. You know, area, in other words, you could say this area here. Look at that area underneath the curve as the ROC curve gets closer and closer to the upper left-hand corner. What's happening to the area? Is it increasing or decreasing? It's increasing, yes. So another way to think about it is that the more area that you have underneath your curve, the better the classification method. And in fact, what you will very frequently see, especially in medical diagnostic tests, when they're trying to come up with a new test to detect disease, you will see something listed as AUC, area underneath curve. The higher that is, the better, let's say, overall the diagnostic test is. Do some erasing here. So that's kind of an overall way to determine how good a particular method is. But sometimes, too, you will see this. Suppose I have another ROC curve. Now, it is supposed to be curvy there. It's not supposed to be jumping up and down. You see the curves cross there. Well, you know, in this situation, let's say you had two different classification methods, one represented by my red mark and one represented by the purple line. Well, which one's better? It depends. You know, you could look at area underneath the curve to make a judgment. But if you're really, really concerned about a particular sensitivity or specificity level, let's say you want extremely high sensitivity, in this case, then the purple curve would be better, because that's going to allow you to get that high sensitivity without having so many false positives. Any questions about that? A lot of stuff I'm talking about right now would be great short answer questions on a test. Okay. Let's say that I want to have a classification method that has extremely high sensitivity. You know, so maybe I want 0.95. Well, at 0.95, which line has the corresponding lower false positivity or lower 1 specificity rate? It's the purple line versus the red. And so in that case, if I'm using that as a judgment of deciding which classification method to use, then area underneath the curve is not necessarily as important as, you know, taking a look at, well, where does 0.95 intersect on that point? You also see another line on there called line for chance accuracy. What do you think that means? Look where it's drawn. So for example, if I look at 0.4 for sensitivity, I get 0.4 for 1 specificity. So what that basically means is this. Think of, think of it, we're looking at conditional probabilities here. The probability that you are going to say something's classified as positive, given that it's truly positive, is 0.4. The probability that you say something is going to be classified as negative, given it is truly, oh, hold on, let me make sure I got that right. Sorry, I said that wrong. We'll start over. It's very easy to get tongue-tied when you're talking about positive, negatives, and true positives, false positives. Anyway, sensitivity. The probability that's a true positive. Oh, I said that wrong. There are other probabilities too that one has to worry about. We're focusing on sensitivity and specificity, but there are other things called a predictive positive level and a negative predictive positive level. Okay, let's try this one more time. I might have to edit this out of the video. So the probability that you classify something as positive, given that it is a true positive, is 0.4 and how I drew that. The probability that you classify something as positive, given that it is truly negative, it's also 0.4. Notice they're exactly the same. So essentially, it's like flipping a coin, a non-biased coin, and how you are saying positive or negative here, because you have exactly the same conditional probability that it is. And so what that means then is that if you ever had a ROC curve somewhere down here, well, it's not even worthwhile to use that classification method. If you had an ROC curve that's above here, somewhere above, then at least you're getting some benefit to using then this classification method. Let's also talk about one other thing with this plot. So here's my sensitivity. Notice I have a second y-axis here, the false negative probability. Notice it goes from 1 up to 0. Why? Well, it's the complement that we just got done talking about. Also, take a look at this x-axis. I have a second x-axis up here that goes instead of from 0 to 1, 1 to 0. It's the true negative probability, which would be specificity. So you might be thinking, well, geez, I'm kind of ignoring some stuff by only looking at sensitivity versus 1 minus specificity. No, I'm not. Because this plot simultaneously gives you a plot of the 1 minus the sensitivity versus the specificity. So that's kind of cool that that happens. Okay, so this is an ROC curve. Now let's look at that in the context of the place kicking data set. Okay. First of all, what would the sensitivity be in words for the place kicking data set? It's the probability of a success, classified as a success, given it is truly a success. Specificity, the probability of a classified as a failure, given that it truly was a failure. Okay, so that's the sensitivity and specificity in this context. So the first thing that we have to do then, in order to get to the ROC curve, is that we have to find the estimated probability of success for our place kicks. There's a few different ways to do that. First of all, just for your observed observations itself, there's a fitted.values component of mod.fit where we store the stuff from GLM. And, I guess we already saw that, sorry. And so those are the estimated probabilities for all 1,425 observations in the data set. Another way to get at those probabilities is to use the predict function. You saw that with the LM function in the past. You say simply the first argument, mod.fit, object equal mod.fit, and then you say type equal response, which tells R you want the predicted pi values. So I put then an object called pi.hat, and those are the estimated probabilities of success. Excuse me. Now let's say we want to work with the validation data set then. We can use the same syntax with the predict function, but add one additional thing. Instead of going with the default, which would be just for the observations in the original data set itself, now I use the new data argument, which allows me to specify any other observations that I want to look at. In this case, with the validation data set. And this is going to give me then, I'm going to put then pi.hat.v, the estimated probability of successes for the validation data set. So for example, for the second observation, the estimated probability of success was 0.66. Now that we have these estimated probability of successes, we can apply a cutoff probability so that we can come up with a prediction of success or failure. So I'm going to create an object called cutoff, set it equal to 0.5. And then to do the prediction, simply use an if-else function that we've seen in the past. Say test equal, is my pi hat greater than the cutoff? If so, I'm going to classify it as a success, a y equal 1. Otherwise, I'm going to classify it as failure as 0. Do that with the original data set and do that with the validation data set. So, for example, if I do head pred.good, there we go. All the first 6 are predicted as successes. That should make sense. Take a look at all these very high probabilities up there. Okay. Now that I have successes and failures predicted, I want to look at, well, how good is my statistical method here? So, remember my summarize.class function from discriminant analysis and the nearest neighbor classification? I can apply this exact same function here to summarize, to come up with a summary table of the true values versus their classifications. So I'm going to do that. Actually, let me just go over here to Word, because I've already done that. And then I can write on this. So for then the actual model, the actual modelability or the actual training data set itself, this is what I get. An overall correct classification rate of about 89%. So this 0.9897 that we see in this table here, what will be then a word for what this probability represents? This is my sensitivity. So my sensitivity is 0.9897. Then the 0.11 is my specificity. So you can see my sensitivity is extremely high, 0.99, great. But my specificity is only 11%. Note that what I just did here, in terms of calculating these accuracy measures, is an example using resubstitution. Because notice what I did here. For my actual data set itself, I got the pi hats for the observations. I didn't take any observations out. I just looked at the observed observations, got their corresponding pi hats, and then calculated these accuracy measures. So this is an example of resubstitution. And we know that this is not ideal to typically look at in terms of accuracy. Let's look at the validation data set then. So I use summarize.class again. My original or my observed classifications or observed successes and failures are in the 9th column of the valid data set. And then my classifications were calculated and put into pred.good.v. And this is what I get. My sensitivity is now about 97%. My specificity is about 8%. Come on, make a T. There we go. My overall correct classification rate is about 85%. So what we're seeing here is somewhat actually similar results to what we were getting in the past. Well, what would happen, though, if I changed my cutoff probability? Are things going to improve? Well, let's try it. How about we just try cutoff probability of 0.7, just to see what would happen. So what that means then, in terms of coding, all I need to do is change that 5 to a 7 and run exactly the same code. Okay? Very simple. And this is what I get. My sensitivity now goes down. It's now 0.91. This is resubstitution. Why does it make intuitive sense for why it's going down? Exactly. So there was some stuff that I'm missing that were successes before. that had a probability between 0.5 and 0.7. In other words, I like to think of it this way, that I have a higher threshold in order to pass before I can say, yes, indeed, that is going to be a positive. And because I have that higher threshold, I'm going to miss some stuff. But look what happens to my specificity. It shoots up to about 0.48. And you should think of it from then the other point of view. Well, why is this now higher than what it was before? I'll let you do that on your own. My overall correct classification rate is 0.86, so actually my overall rate has actually dropped a little bit. For the validation data set, this is what I get. Sensitivity 0.88, specificity 0.61. Overall correct classification rate is 0.84. So as we will see shortly then, to do an ROC curve, basically you're just doing what we just did here for 0.5 as a cutoff probability, for 0.7 as a cutoff probability. You're doing that a whole bunch of other times so that you essentially can get a grid of points representing sensitivities and specificities. And then you plot them. You'll see that very shortly. But before we do that, let's talk about cross-validation. Now we know that cross-validation is going to be better than resubstitution in terms of its measure of how good your classification method does. So it would be nice to apply cross-validation here. What does that mean essentially? Well, let's talk about the first observation. Well, you would take that first observation out of the data set, you re-estimate your model, get the pi hat then, using this re-estimated model for the first observation, and then classify as a success or failure depending upon what your cutoff probability is. Then go to your second observation after you put the first observation back in the data set. Go to your second observation, remove it, re-estimate the model, get then the pi hat for this observation that was removed from the data set, and then classify. So if I have 1,425 observations, how many different models am I estimating? 1,425. So you can see it could be kind of time consuming. Also, unfortunately here in R, there is not a function that automatically does it for you. Or at least I wasn't able to find it. It's not that big of a deal. It's really easy to write your own function, so that's what we're going to do next. Okay, so here's my function. I decided to call it CV, or cross-validation. I'm going to pass in just 2 bits of information. The model, in terms of what's the actual model I want to estimate, and then the data set name. So the first thing I'm going to do inside the function is find my number of observations. And then the rest of the code is basically what I had just described to you. It allows me to take one observation out at a time, estimate the model, predict pi hat for that removed observation, and then come up with a predicted classification. Or I'm sorry, this actually just gives me my pi hat out. So it doesn't actually tell me success or failure. We'll do that shortly. What it does is just give me my pi hat. So, as you might expect, I need a way to store all these pi hats that I'm going to be calculating. So I create an object called pi.hat.cv. I could create a matrix to store them in. And since I only need to look at basically essentially one column of information in my matrix, these new pi hats, I decided to create what's called a vector in R. To create a vector, I'm not for sure if we've actually done this in this manner before, I can use the function called numeric. And the length of it is going to be my sample size. Then I use a for loop, as we've done before. I re-estimate my model. Notice what happens in my data argument here. I remove the rth observation while I'm re-estimating the model. And then I'm going to predict then for that removed observation what the actual pi hat is. So notice my new data argument that we used with the validation data set before. I have data.set just look at the rth observation there. I get the pi hat out. I put it into my pi.hat.cv, the rth component. And then I return in the end pi hat.cv. I would run this in class, but it would take a couple minutes, and we only have about 10 minutes left, so I'm not going to. Of course, you're expected to run this on your own. And so to call the function then, I say CV, I put in my model that we saw before, I put in my data set, I save my result into something called save.cv, set my cutoff probability, use my if-else function to make the classification. And then I use summarize.class to summarize the results. This is what I get. Here's my sensitivity, and here's my specificity. Very, very similar. I'm using cutoff of 0.5 here. Very, very similar to what we saw before with resubstitution. So I actually asked that. So why would you expect resubstitution and cross-validation to be quite similar here? The sample size, exactly. Just removing one observation at a time when you have a sample size of already 1,425, it's not going to have that much of an effect. So because I'm just simply going to use a resubstitution for the rest of this, this section. Okay, so how can we do then these ROC curves? Finally, well, there are a number of packages in R designed to do these ROC curves. What I have found to be the best and easiest to use is a package called ROC-R. And this is a package that you're going to have to actually download and install. Excuse me. I'll make a note to myself here. Unfortunately, there's not just one function that you can use to immediately create the curve for you. You have to actually use, I think it's actually three functions to finally get the actual curve that you need. And so we'll see that very shortly. But before we do that, I need to briefly mention that this package is written in a different way than what we've seen before throughout this course. As I said, the first day of this course, R is based upon an actual computer language called S. And there have been different versions of S written. Most of the stuff that is in R right now is written in what's called S version 3. People often just simply abbreviate that as S3. There are some things in R, though, that's written in S version 4. And again, people refer to this as S4. This particular package is written in S4. Now, in the grand scheme of things, especially for this class, it's not going to mean it's not going to make a big deal for you. But there are some small things that I need to tell you in order for you to understand what some of this code is doing. First of all, if you remember when, for example, when we had mod.fit resulting from the GLM function, GLM is actually written in S version 3, we were able to use mod.fit, $, and then something after it. We could pull information out of mod.fit. Well, when you have an S version 4 object, instead of a $, you use the @ symbol. Okay. Also, if you remember, if I wanted to see everything that was the names of everything that was installed in mod.fit, I could simply use names mod.fit, and that will give you a list of the names of the things that are inside this list. With S version 4 objects, instead, you need to use the function slot names to do the same thing. The reason why is because the components of an object in S version 4 are called slots. It's just terminology. It's just the way it is. S version 4 has been out since, I think, the very late 1990s or early 2000s. And while it's been out for over 10 years, still everything is predominantly programmed into R in S version 3. I think people think it's good enough. I mean, there are some small advantages to using S version 4, but for most purposes, S version 3 is good enough. People are most comfortable with it, and so that's why most stuff is programming in S version 3. I'm talking about also, let's say, new packages are typically programmed in S version 3 versus S version 4. But this is an S version 4 package. Okay, so those are the big things that you need to know about S version 4. Now, let's talk about these RLC curves again. To do an RLC curve, the first thing that you need to do is use a function that's in the RLCR package called prediction. And what this essentially does, it gives you your sensitivities and your 1 minus specificities for a whole bunch of different cutoff probabilities. So there is an argument inside of the prediction function called predictions. This is where you can put in your pi hats. So I'm just using the resubstitution method here. So I put in my pi hat that I calculated before. And then in the labels argument, this is where you specify, well, was this truly a success or a failure? So remember the 9th column, PlayStick gave me that information. That's my good variable. And then if you wanted to see the stuff that's stored inside of now save.pred, I can use slot names. And you can see some things names that are kind of familiar, such as, here are my cutoffs. FP stands for false positive rate. False positive, I should say. Then once you do that, then, next you have to use another function inside the package called performance. And this calculates overall performance measures using the information that we had from the previous function. So I say prediction.obj for the first object. I save the stuff from the prediction function, save.pred. And then after that, I specify, well, what overall measures am I interested in? Well, I'm interested in, and this is just the syntax, look at the help for the function. I'm interested in the sensitivity. I'm interested in the FPR, false positive rate. There is another argument you could use in there that we'll look at later called AUC, if you want just the area underneath the curve. Then finally, I can use the plot function with the results that I saved from the performance function, and I can plot my RLC curve. And this is what it looks like. So again, you have sensitivity on the y-axis. You have the 1 minus the specificity on the x-axis, otherwise known as the false positive rate. So if I were to draw the line of chance, there's my line of chance there. You can see, obviously, the RLC curve is above that. So this is saying that there is some benefit, at least some benefit, to using this logistic regression model for prediction, for classifying success or failure. One odd thing about this particular function is that in order to get the grid lines on the plot, it's hard to see, but they are up there. To get the grid lines on the plot, typically when we've used the plot function, we say panel.first equal grid. Well, you can't do that with this function for some reason. I don't know why. And so I can actually use a function right after the plot function called grid to draw the grid lines, and that's what I actually did. Now, quickly here, let's go to page 27 then. Unfortunately, I guess we don't have time. Well, we'll start here next in the next class. This shows you then how you can find what the corresponding cutoff probabilities are. Do note that ROC curves will be on the exam, so they will be on the exam. So please note that. So don't think that you can say, okay, I'm going to blow this off until the final exam. They will be on the exam. Are there any questions? Okay, that's it for today.